were exploring the last frontier, the deep ocean. And during that exploration, they found made an astonishing discovery that changed how we thought about Earth.
Nearly 7 miles beneath the Pacific, NASA found a whole new world, a world unlike anything on our planet. Every expedition overturned another scientific certainty, transforming the deep ocean from an unexplored frontier into the closest known analog for the hidden oceans of Europa and Enceladus. The deeper researchers ventured beneath our own planet, the more Earth itself began to resemble an alien world. So, what's really at the bottom of the ocean? Well, NASA has finally revealed it. NASA was preparing to find aliens. NASA's deep ocean research was never about searching for strange creatures lurking in Earth's abyss. Instead, the agency's scientists and engineers had their eyes fixed on worlds hundreds of millions of miles away. Long before spacecraft began sending back breathtaking images of Jupiter's moon Europa and Saturn's moon Enceladus, researchers realized that if life existed elsewhere in our solar system, it was far more likely to be hidden beneath ice than walking on a rocky surface. That realization transformed Earth's deepest oceans into the closest testing ground humanity had for exploring alien worlds. The reason becomes obvious when you compare these distant moons with Earth's own abyss. Europa, one of Jupiter's 4 large Galilean moons discovered by Galileo in 1610, is covered by an ice shell estimated to be between 15 and 25 kilometers, or 9 to 15 miles, thick. Beneath that frozen crust lies an immense global ocean, and scientists estimate it may contain more than twice the amount of water found in all of Earth's oceans combined. Unlike Earth, however, that ocean exists in perpetual darkness. No sunlight penetrates the ice. Surface temperatures plunge to around -160 degrees Celsius, yet tidal forces generated by Jupiter's immense gravity continually flex Europa's interior, producing enough heat to keep its hidden ocean liquid. If life exists there, it has likely never seen sunlight. But how is that even possible? Well, NASA would soon answer this question. Meanwhile, Saturn's moon Enceladus proved even more astonishing. When NASA's Cassini-Huygens spacecraft repeatedly flew past the tiny moon between 2005 and 2017, its instruments detected towering geysers erupting from fractures near the South Pole. Those plumes weren't simply water vapor. They contained liquid water, molecular hydrogen, methane, carbon dioxide, silica nanoparticles, salts, and a variety of organic compounds. The very ingredients scientists associate with environments capable of supporting life. Molecular hydrogen, in particular, excited researchers because on Earth, it serves as an energy source for microbes living around hydrothermal vents. Without drilling through kilometers of ice, Cassini sampled material coming directly from an alien ocean. That raised an entirely different challenge. Suppose NASA eventually sends a submarine beneath Europa's ice. How would it survive? Earth's oceans already provide a glimpse of the problem. GPS signals cannot penetrate seawater. Radio waves travel only short distances underwater. Sunlight disappears within a few hundred meters, leaving complete darkness below roughly 1,000 meters. Human divers are useless in the abyss, and rescue missions are practically impossible. A robot operating beneath Europa's ice would face every one of those obstacles simultaneously, except there would also be a 30 to 50-minute communication delay between Earth and Jupiter, making real-time control completely impossible. Those engineering realities explain why NASA became deeply involved in underwater robotics. Rather than simply building stronger submersibles, engineers began developing machines capable of thinking for themselves. One of the most ambitious examples is Orpheus, an autonomous underwater vehicle developed with support from NASA's Jet Propulsion Laboratory and academic partners. Instead of relying on GPS, Orpheus navigates by recognizing rocks, ridges, and geological landmarks across the seafloor, much like a hiker memorizing a trail through a dark forest. NASA's astrobiologists realized that Earth's deep ocean contains environments remarkably similar to those expected beneath Europa and Enceladus. Sounds unbelievable, doesn't it? But one dive at a time, NASA uncovered just how true this is. into Earth's final frontier, the ocean that still defies humanity. There is a place on Earth so hostile that even today, reaching it is rarer than walking on the moon. Since the Apollo program ended in 1972, only 12 astronauts have set foot on the lunar surface, and remarkably, even fewer people have descended to Challenger Deep, the deepest known point of the Mariana Trench in the western Pacific Ocean. Located about 10,935 meters, or nearly 36,000 feet below sea level, Challenger Deep remains one of the least visited places on the planet. That mystery becomes even more astonishing when you realize how little of our own planet we actually know. Oceans cover about 71% of Earth's surface, spanning roughly 361 million square kilometers. Yet scientists estimate that only a tiny fraction of the deep sea floor has been directly observed with cameras or human-operated vehicles. While satellites have mapped the surfaces of Mars, Mercury, and even distant Pluto in remarkable detail, the landscape beneath Earth's deepest oceans remains largely unknown. Entire mountain ranges, underwater volcanoes, deep trenches, and ecosystems await discovery. But why? Well, the reason is simple. Pressure. Water is unforgiving. For every 10 meters of depth, pressure increases by approximately 1 atmosphere. At Challenger Deep, that reaches nearly 1,100 atmospheres, more than 16,000 pounds per square inch. To picture that force, imagine the weight of about 50 jumbo jets pressing down on an area the size of a human body. At those depths, ordinary steel bends, glass shatters instantly, and tiny imperfections in metal can become catastrophic points of failure. Thus, exploring the abyss is far more difficult than many people realize. Cameras require specially designed pressure housings. Electronic circuits must be sealed against both seawater and crushing force. Batteries behave differently under extreme pressure, while cables, stretching thousands of meters, become increasingly vulnerable to damage. Even powerful floodlights illuminate only a few meters through the darkness. Danger is constant. In fact, on May 10, 2014, during a scientific expedition to the Kermadec Trench, northeast of New Zealand, researchers deployed Nereus, one of the world's most sophisticated autonomous underwater vehicles. Built by the Woods Hole Oceanographic Institution at a cost of between $8 million and $14 million, Nereus had already achieved what few machines ever had, including successful dives to Challenger Deep. During its descent to nearly 10,000 meters in the Kermadec Trench, communication suddenly stopped. Apparently, the immense pressure caused a catastrophic implosion, scattering fragments of the vehicle across the seafloor. The destruction of Nereus forced scientists to confront an uncomfortable reality. Building a single, extraordinarily expensive machine capable of reaching the deepest ocean also meant placing an entire research program at risk every time it descended. Thus came a new generation of underwater explorers, including Orpheus, an autonomous robot developed through collaborations involving NASA's Jet Propulsion Laboratory and leading oceanographic institutions. Instead of depending on continuous communication with operators aboard a ship, Orpheus was designed to think independently. Since GPS signals cannot penetrate seawater, the robot navigates by recognizing features on the seafloor itself: rocks, ridges, slopes, and other geological landmarks. NASA understands that a future submarine exploring the hidden ocean beneath Jupiter's moon, Europa, or Saturn's moon Enceladus, will face nearly identical challenges. There will be no GPS beneath kilometers of alien ice, no sunlight for navigation, no reliable radio communication through water, and no possibility of astronauts rushing in for repairs. Every robotic decision will have to be made independently. But what did they find at the bottom of our oceans? Let's dive into that now. Everything science believed about life was wrong. In 1977, an expedition to a remote volcanic ridge in the Pacific Ocean stumbled upon something that should not have existed. Instead of finding a barren seafloor, scientists discovered a thriving metropolis of life flourishing nearly 2,500 meters, or about 8,000 feet, beneath the surface, in total darkness. The discovery occurred along the Galapagos Rift, part of the East Pacific Rise, during a mission involving the deep submergence vehicle Alvin, operated by the Woods Hole Oceanographic Institution. On February 17, 1977, geologist Jack Corliss and his colleagues expected to study volcanic activity on the seafloor. Instead, Alvin's lights illuminated enormous white tube-like structures clustered around towering mineral chimneys. Surrounding them were giant clams, crabs, mussels, fish, octopuses, and dense swarms of unfamiliar organisms. Not a ray of sunlight could reach these depths. So how were these communities surviving? You see, rising from fractures in the Earth's crust were hydrothermal vents, natural openings where seawater seeped deep underground, became superheated by magma, and erupted back into the ocean carrying dissolved minerals. Some of these black smokers expelled fluids exceeding 370 degrees Celsius, or about 700 degrees Fahrenheit. Under normal atmospheric conditions, water would instantly boil into steam at those temperatures, but nearly 250 times the pressure found at sea level kept the water in liquid form, allowing it to blast from the vents like underwater geysers. As the mineral-rich fluids met the freezing seawater, metals precipitated instantly, forming towering black chimneys that could grow several stories high. These ecosystems are powered by chemosynthesis. Specialized bacteria extracted energy from hydrogen sulfide, methane, and other chemicals emerging from Earth's interior, converting them into organic matter, much the way plants use sunlight during photosynthesis. Among the most bizarre inhabitants of this region were giant tube worms belonging to the species Riftia pachyptila. Growing up to 2.4 meters, or nearly 8 feet long, these striking red and white animals had no mouth, no stomach, and no digestive system whatsoever.
These annelids weren't known prior to the 1970s. Scientists didn't even believe they could exist. The hydrothermal vents they inhabit were thought too extreme to support life.
Instead, inside a specialized organ called the trophosome lived billions of symbiotic bacteria. The worms absorbed hydrogen sulfide, oxygen, and carbon dioxide directly from the surrounding water, delivering these chemicals to the bacteria, which produced nutrients through chemosynthesis. The bacteria fed the worms, while the worms provided them with a safe home and a steady supply of chemicals. Other creatures evolved equally remarkable adaptations. Around hydrothermal vents in the mid-Atlantic ridge and the Caribbean, scientists discovered dense colonies of blind shrimp, including Rimicaris xoculata. Conventional eyes would have been useless in complete darkness, so evolution took a different path. These shrimp possess highly specialized light-sensitive organs on their backs, capable of detecting the faint infrared glow and thermal radiation produced by the scorching vent fluids. Combined with sensitivity to chemical gradients, these adaptations allow them to remain in a narrow Goldilocks zone, close enough to access food-producing bacteria, yet far enough away to avoid being cooked alive. Tiny bacteria form the base of the ecosystem. Tube worms, mussels, and clams rely directly on those microbes, while crabs, fish, octopuses, scale worms, and other predators occupy higher levels of the food chain. But why does this matter to NASA? Well, you see, if life on Earth can thrive in crushing pressure, complete darkness, toxic chemicals, and near-boiling water, then sunlight is no longer a requirement for habitability. However, what scientists found next was even harder to believe. Earth's hidden alien worlds already exist beneath our feet. One of the first surprises came from methane seeps, sometimes called cold seeps. Unlike hydrothermal vents, these environments are not heated by magma. Instead, methane and other hydrocarbons slowly leak through cracks in ancient sediments on the seafloor, often thousands of meters below the surface. Scientists first recognized their ecological importance during the 1980s in locations including the Gulf of Mexico, the Pacific margin, and the Atlantic Ocean. Temperatures remain close to freezing, typically around 4 degrees Celsius, yet life flourishes. Here, bacteria consume methane through chemical reactions rather than sunlight. In some regions, methane escaping from beneath the seabed even freezes into methane hydrate, an ice-like substance that burns if ignited after being brought to the surface. Those microscopic bacteria support surprisingly large animals. Giant mussels, some exceeding 30 centimeters in length, harbor methane-consuming bacteria inside their gills. Much like tube worms host chemosynthetic microbes around hydrothermal vents. Thick colonies of clams, tube worms stretching over 2 meters long. Crabs, sea cucumbers, and fish gather around these seeps despite the surrounding darkness and toxic chemistry. Some tube worm colonies are believed to survive for more than 200 years. Then, at the bottom of the Gulf of Mexico, researchers encountered what appeared to be actual lakes, complete with shorelines, waves, and beaches, except they existed underwater. These formations, known as brine pools, contain water up to 5 times saltier than the surrounding ocean. Because the dense brine is heavier than normal seawater, it settles into depressions on the sea floor, creating sharply defined boundaries that resemble coastlines. The largest known pools measure hundreds of meters across. From a distance, the scene looks uncannily familiar until fish swimming into the lake suddenly lose buoyancy, become disoriented, and often suffocate or die because the water contains little oxygen and high concentrations of toxic chemicals such as hydrogen sulfide. Yet even these lethal pools turned out not to be barren. Around their edges, where ordinary seawater mixes with the dense brine, scientists found thick microbial mats resembling white carpets spread across the seabed. Those microbes again form the base of a chemical food web. Giant mussels, tube worms, shrimp, and specialized crabs crowd around the margins, feeding either directly or indirectly on bacteria that convert methane and sulfides into energy. Then there's the Lost City hydrothermal field. Discovered in December 2000 during an expedition led by researchers from the University of Washington, the site lies on the Atlantis Massif in the mid-Atlantic Ocean, about 15 kilometers west of the Mid-Atlantic Ridge. Unlike the famous black smokers, Lost City is not powered directly by volcanic heat. Instead, seawater reacts chemically with mantle rocks through a process called serpentinization, producing hydrogen, methane, and heat without requiring active volcanism. Towering carbonate chimneys, some reaching nearly 60 meters or about 200 feet tall, have been venting continuously for at least 120,000 years. As extraordinary as these underwater ecosystems were, scientists eventually discovered that some of Earth's most isolated life was buried deep inside the planet. In South Africa's Mponeng gold mine, southwest of Johannesburg, researchers drilling nearly 3 kilometers below the surface recovered groundwater that had remained isolated for millions of years. Inside it lived microorganisms unlike anything expected at such depths. Among them was the bacterium Candidatus desulforudis audaxviator, first described in 2008. Remarkably, this organism can survive almost entirely on its own. It obtains energy not from sunlight or organic matter, but from hydrogen and sulfate produced when natural radioactive decay from uranium, thorium, and potassium splits nearby water molecules in surrounding rock. The ocean is teaching NASA where to search for alien life. For much of the space age, NASA's scientists assumed that if life existed elsewhere, it would probably resemble life on Earth's surface. Organisms relying on photosynthesis, moderate temperatures, and liquid water warmed by a nearby star. Planets too cold or too far from the sun were considered poor candidates. But now, that assumption has been upended. This has dramatically expanded the number of places that might support life. Mars remained an important target because orbiters and rovers had uncovered overwhelming evidence that rivers, lakes, and perhaps even an ocean existed there billions of years ago. Today, radar observations and geological evidence suggest liquid water may still exist beneath the Martian surface, protected from the harsh radiation that bombards the planet above. If microbes on Earth can survive kilometers underground without sunlight, feeding on chemical reactions inside rock, then similar organisms could theoretically persist beneath Mars, even after its surface became cold and dry. What once seemed impossible now had a real terrestrial example. Even more exciting were the icy moons orbiting the giant planets. Jupiter's moon Europa, discovered by Galileo Galilei in 1610, quickly rose to the top of NASA's priority list. Beneath an ice shell, estimated to be 15 to 25 kilometers thick, lies a global saltwater ocean that may contain more than twice the volume of water found in all of Earth's oceans combined. Scientists believe Europa's interior is continually flexed by Jupiter's immense gravity, generating heat through tidal forces. That process could drive hydrothermal activity on the Moon's seafloor, remarkably similar to the black smokers and lost city hydrothermal systems found in Earth's deep oceans. If chemical energy powers life here, why not there? Then there is Enceladus, Saturn's sixth largest moon, only about 504 kilometers across. During multiple flybys between 2005 and 2017, NASA's Cassini spacecraft flew directly through enormous plumes erupting from fractures nicknamed the Tiger Stripes near the Moon's south pole. The spacecraft detected water vapor, molecular hydrogen, methane, carbon dioxide, ammonia, salts, silica nanoparticles, and a range of organic compounds. The presence of molecular hydrogen proved particularly significant because, on Earth, hydrogen fuels microbial communities living around hydrothermal vents. Cassini's discoveries strongly suggested that Enceladus possesses an active ocean interacting with a rocky sea floor. This makes it one of the most promising habitats for extraterrestrial microbial life in the solar system. Saturn's largest moon, Titan, complicated the picture even further. Unlike Europa and Enceladus, Titan has a dense nitrogen-rich atmosphere and rivers, lakes, and seas. Not of water, but of liquid methane and ethane. Beneath its frozen crust, however, scientists believe Titan also harbors a vast subsurface water ocean. Although its surface chemistry differs dramatically from Earth's, Titan is rich in complex organic molecules formed by sunlight interacting with atmospheric methane. These compounds continually rain onto the surface, making Titan one of the most chemically active worlds known. NASA's Dragonfly mission, scheduled to arrive in the 2030s, will explore this remarkable moon, searching for clues about prebiotic chemistry that may resemble conditions on the early Earth. But it only gets stranger from here. The discovery scientists still can't fully explain. Just when scientists thought the deep ocean had exhausted its ability to surprise them, it produced another mystery.
Picture a lump of rock about the size of a potato. Now pack it with some of the most valuable metals on Earth, like nickel, cobalt, and other minerals known as rare earth elements.
At the bottom of the Pacific Ocean, nearly 4,000 meters, or about 13,000 feet below the surface, researchers expected to watch oxygen slowly disappear. That was the entire purpose of their experiment. Deep-sea animals and microbes consume oxygen, and in complete darkness, with no plants or algae performing photosynthesis, there should be no way to replace it. Instead, their instruments recorded the exact opposite. Oxygen concentrations began rising. The observations came from scientific expeditions conducted between 2021 and 2024 in the Clarion-Clipperton Zone, or CCZ, a vast abyssal plain stretching roughly 4.5 million square kilometers between Hawaii and Mexico. The region is famous for its enormous fields of polymetallic nodules, potato-sized mineral deposits rich in manganese, nickel, cobalt, copper, and iron. Because these metals are essential for rechargeable batteries and other modern technologies, the CCZ has become the focus of intense interest from deep-sea mining companies.
The nodules were discovered more than a century ago. Now, new technology has triggered a fierce competition to go get them. These metals are critical for modern life, cell phones, electric cars.
But before mining could begin, marine scientists were studying how these untouched ecosystems functioned. The research team deployed sealed benthic chambers onto the seafloor to measure how much oxygen was being consumed by deep-sea organisms living in the sediment. Once the chamber enclosed a section of seabed, oxygen should gradually decline as microbes and animals continued breathing. Instead, several experiments showed oxygen levels increasing over time. The measurements contradicted decades of biological understanding. There was no sunlight at nearly 4,000 meters. Photosynthesis was impossible. There were no obvious chemical reactions known to generate oxygen under those conditions. If the instruments were correct, something entirely unexpected was happening on the ocean floor. Naturally, the scientists suspected faulty equipment. Oceanographic instruments operate under crushing pressures approaching 400 atmospheres, and even minor calibration errors can produce misleading results. Rather than announcing a revolutionary discovery, the researchers repeated the experiments. They deployed fresh sensors. They used different analytical techniques. They tested additional chambers in separate locations. Yet, the pattern persisted. Oxygen repeatedly appeared where none should have been produced. According to the researchers, some chambers recorded oxygen concentrations rising to several times the expected background changes. Instead of eliminating the mystery, every additional test made it more difficult to dismiss. The team then considered another possibility. Perhaps an unknown microorganism was somehow generating oxygen through a biological process unlike ordinary photosynthesis. To investigate, they carried out experiments designed to suppress or eliminate microbial activity using chemical treatments. If living organisms were responsible, oxygen production should have stopped. Yet oxygen continued appearing even when biological explanations became increasingly unlikely. The evidence pointed toward something non-living. Attention shifted away from microbes and toward the most abundant objects scattered across the seabed: the polymetallic nodules themselves. These nodules are geological oddities in their own right. Growing only a few millimeters every million years, they slowly accumulate dissolved metals from seawater over tens of millions of years. Many nodules lying on the Pacific seafloor today began forming long before the dinosaurs evolved. When researchers examined them more closely, they found that individual nodules could generate tiny electrical potentials. The voltages were extremely small, far below those of a household battery, but measurable nonetheless. That observation inspired an intriguing hypothesis. If enough electrical potential existed across the surfaces of these metal-rich rocks, perhaps they could drive electrochemical reactions capable of splitting seawater molecules into hydrogen and oxygen, a process similar to electrolysis. The idea quickly became known as the dark oxygen hypothesis because it proposed oxygen generation without sunlight or photosynthesis. If correct, the implications would extend far beyond marine biology. For billions of years, scientists have regarded atmospheric oxygen as one of the strongest potential biosignatures when searching for life on other planets. The logic seemed straightforward. On Earth, oxygen exists in abundance because plants, algae, and cyanobacteria continually replenish it through photosynthesis. Detecting oxygen in the atmosphere of an exoplanet has therefore been considered a promising indication of biological activity. But if ordinary geological processes can produce oxygen under certain conditions, that assumption becomes far less secure. That does not mean the hypothesis has been proven. In fact, it remains one of the most actively debated topics in marine geochemistry and astrobiology. Some researchers argue that the observed oxygen increases may still result from subtle measurement errors, contamination, or previously unknown microbial processes rather than electrochemical reactions. Others question whether the voltages measured on individual nodules are sufficient to sustain significant oxygen production in natural environments. Independent laboratories are now attempting to reproduce the findings under controlled conditions because extraordinary claims require equally extraordinary evidence. Regardless of the final explanation, the discovery has intensified concerns about deep-sea mining in the Clarion-Clipperton Zone. The International Seabed Authority has been evaluating regulations for commercial mining, while dozens of exploration contracts have already been issued to various nations and companies. Mining operations would remove billions of these polymetallic nodules, destroy habitats that have taken millions of years to develop, and generate sediment plumes capable of spreading across vast areas of the seafloor. Scientists have already documented that many deep-sea animals, including sponges, corals, sea cucumbers, brittle stars, and countless microbial communities, live directly on or around the nodules. Some species appear to exist nowhere else. We may have been looking in the wrong direction all along. Perhaps the biggest surprise is that humanity has barely begun exploring the oceans. While astronauts have photographed entire planets from orbit and spacecraft have mapped the surfaces of Mars, Mercury, and Pluto in extraordinary detail, the vast majority of Earth's deepest seafloor remains virtually unknown. One of the first things explorers notice after entering the deep ocean is that darkness does not mean the absence of light. Instead, the abyss constantly flickers with flashes of blue, green, and occasionally red, produced by living organisms themselves. Scientists estimate that roughly 75 to 90% of animals living in the open ocean below about 200 meters possess some form of bioluminescence. Dragonfish use glowing lures to attract prey. Anglerfish dangle illuminated appendages in front of enormous jaws. Comb jellies produce shimmering waves of color, while certain squid eject clouds of glowing mucus to confuse predators. Even tiny plankton can erupt into brilliant flashes when disturbed. Then there's an equally remarkable phenomenon known as marine snow. Every day, an endless shower of microscopic debris drifts downward from the surface. Dead plankton, fish scales, fecal pellets, mucus, fragments of shells, and bits of decaying organic matter. Individual particles may take weeks or even months to reach the abyss, descending through nearly 4 kilometers of water before finally settling on the seafloor. For countless deep-sea animals, this slow snowfall represents the primary food supply. Sea cucumbers, brittle stars, worms, crustaceans, and microbial communities survive by collecting these tiny particles one by one. Some creatures, however, evolved to survive conditions once believed impossible for complex vertebrates. The deepest known fish, the Mariana snailfish, or Pseudoliparus swirae, was formally described in 2017 after being observed swimming at depths exceeding 8,000 meters inside the Mariana Trench. At those depths, pressure exceeds 800 atmospheres, enough to crush ordinary bones and disrupt proteins essential for life.
It was at over 5 miles or 8 kilometers deep. Usually that would be a problem because the pressure there is about 800 times that at the surface, so strong that it can force proteins in the cells out of shape, which could be lethal to the fish.
Yet the snailfish possesses unique biochemical adaptations, including unusually stable proteins and high concentrations of trimethylamine N oxide, a compound that helps prevent cellular structures from collapsing under immense pressure. Just a few decades ago, many scientists believed vertebrates simply could not survive below about 6,000 meters. Nature quietly proved otherwise. The Seabed 2030 initiative, launched by the Nippon Foundation and the General Bathymetric Chart of the Oceans, or GEBCO, aims to produce a complete map of the global seafloor by 2030. But even detailed maps cannot reveal the biology living there. In many places, the first close-up images have yet to be taken. Every major discovery has forced scientists to rethink another supposedly universal rule. Hydrothermal vents demonstrated that sunlight is not essential for ecosystems. Methane seeps proved that hydrocarbons could fuel complex food webs. Brine pools showed that life could flourish beside waters toxic to most organisms. Deep underground microbes revealed that radioactive decay can sustain life in total isolation. The controversial dark oxygen observations suggested that even oxygen production itself might not require biology under certain conditions. Individually, each discovery challenged one scientific assumption. Together, they completely transformed the definition of a habitable environment. That transformation may ultimately become NASA's greatest achievement. Decades of deep ocean research have revealed that life is astonishingly adaptable. Given liquid water, an energy source, and suitable chemistry, it repeatedly finds ways to survive in environments once dismissed as impossible. That realization reshaped the search for extraterrestrial life, redirecting attention from warm, Earth-like planets toward icy moons, underground aquifers, and hidden oceans scattered throughout the solar system. Europa's buried ocean no longer appears quite so unimaginable after discovering hydrothermal ecosystems thriving beneath Earth's abyss. Enceladus's hydrogen-rich plumes resemble the chemistry supporting microbes around submarine vents. Even Mars, once written off as a frozen desert, now looks more intriguing because Earth's own deep biosphere has shown that life does not necessarily belong on a planet's surface. Could we be closer than ever to making first contact? For now, all we can do is wait and see. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.